Hello students of statics, this is Dr. Dan Baker, and today's video is going to focus on another technique to solve truss problems. And this is called the method of sections. You may recall from the method of joints video that I talked about that not only is an entire truss in equilibrium, but also every joint is in equilibrium, every member is in equilibrium, and every section is in equilibrium. Okay, so this idea of cutting a truss into sections looks something like the following. Okay, so let's create a truss. We need to have this be a simple truss, so we put some cross pieces here to make it into triangles, noting that all these joints are still pins. All right, there we go. We do need some supports. Let's go with a pin up here. Hand-drawn pins tend to be triangles. Rollers tend to be circles, so a pin at the top, a roller at the bottom. Letter these points A, B, C, D, E, F, and G. Okay, so there are my joints. Now, we're method of joints with kind of a brute force method that you basically had to go through and sum forces at every single joint, and it was just a whole bunch of angles and kind of working through joint by joint by joint. Method of sections is more strategic. Okay, so let's say instead of solving for all of the members across this entire body, that we only want to solve for FG. Okay, so we want to find the force in FG. So we could definitely start with method of joints. Now let me go ahead and add our one external forces out here at point A. And so this is 1,000 newtons or 1 kilonewton there at A. And you could do method of joints at A, you could go to B, you then could go, you could go to G, right? So with 3 free body diagrams, probably 6 equations, we could get to our answer. What if I told you that we could actually solve for FG with a single free body diagram and a single equation? Okay, and the way we're going to do that is we are going to cut, in honor of a colleague of mine at Cal Poly San Luis Obispo, we call this the blue saw. So we'll section here, cutting through with the blue saw. And really what we're going to do is we're going to cut this truss into 2 separate free body diagrams. Okay, so the left end of this truss would look like the following. There's point B, we cut off that member there, and we cut off this member here, and we cut off this member here. So adding my forces, here is my 1,000 newtons. And then I need to basically show these internal forces. Okay, so this one I'm going to call BC, this one here I'm going to call CG, and down here is the one I'm looking for, FG. Now it doesn't technically matter if you label these in alphabetical order. You could also say like BC is the same thing as CB, because in this context it's a 2-force member, right? And so if it's a 2-force member, the force that B is pulling on C is exactly equal to the magnitude of the force C is pulling on B, right? So if they're both in tension, they're both going to be in tension. Anyway, so the labeling of these is a little bit flexible, but you do need to label them independently because all 3 of these different exposed forces could have different values. Okay, so there's one free body diagram. The other free body diagram that I could draw would be the right end of this system. So here's my cut member coming over to joint D. Can make a square out of that one. Horizontal piece here on the bottom, and then a small cut piece here. Okay, so it shouldn't be a surprise that I'm going to draw equal and opposite forces because it's, like I said, essentially the same member that I cut, just the opposite end. But also here, I need to add all of my reaction forces. I also, just to be complete here, let me include that member, which is FD. Now, I didn't cut that one, so I don't need to expose any forces on it, but it does need to keep that body rigid. Make sure I have some triangles. So here's a pin force, dy dx, and a horizontal force from that roller, EX. All right, so two separate, and they're basically independent free body diagrams. Take your pick on which one you'd like to use. I like the one on the left. The reason I like the one on the left is I can solve for my three unknowns directly, right? I don't need to do anything else. I have one known value on that free body diagram. I have three or fewer unknowns. Over here, I have six unknowns. It doesn't mean I still couldn't solve for FG. It's just that I would need to solve for dx and dy and ex first. And the way I would do that is I'd actually create a free body diagram of the entire truss, right? Treating this entire thing like a rigid body. I would express all of my external forces, my 1,000 newtons, the roller force here at x, my pin forces here, dx and dy. Okay, and so there I could solve for those three supports. Then I could bring those values into my next free body diagram and solve for my internals. Okay, so the easier method is going to be to use this left end. And just to note that you only need to solve for the supports that are basically on the free body diagram that you're going to use. Okay, so in this case, I didn't have any supports on this left end. Now here's the strategic question. I said that I could solve for FG with one free body diagram. We've identified that. Now where would I sum moments about to come up with one single equation that I then could find the value of FG? Feel free to pause the video until you find that point. Where could I sum moments about that I could solve for FG with one equation? Turns out that that point, I could actually map here the lines of action of all three forces, right? There's my line of action of CG. Here's my line of action of BC. Here's my line of action of FG, okay? So the important points here are where two lines of action intersect. So if I sum my moments up here at point C, my value of FG becomes my only unknown in that equation, okay? So to solve for FG with one equation, we're going to sum our moments at point C equal to 0. Now, it doesn't mean that you couldn't go through a standard set of some force X, some force Y, and pick some other point to sum your moments about and still get the same answer. We're just talking about basically a path to the solution that is the most efficient would be to sum moments around point C. So that's the general idea for method of sections. So now to look at some guidance for method of sections, and I chose to go ahead and type these out versus having to write all of them out and leave any interpretation between my handwriting and your notes. So we want to first get rid of zero force members. And you can also do that with method of joints, quite honestly. So zero force members really just decrease our amount of work. So if you can identify those zero force members, which were discussed in the previous video, it really just simplifies your computations, right? It makes your life easier. We love zeros. Now, as you choose your cut, this is probably the most, between choosing your cut and then identifying points you want to sum moments around, kind of the two most strategic things you'll learn in method of sections. You typically want to cut through the members you're asked to solve for, okay? The only reason you wouldn't want to do that is if cutting through that member meant you cut through 4 or more members, okay? If we can cut through 3 members, it basically leaves us 3 unknowns, which we know in a 2-dimensional equilibrium system, we can have 3 equations and solve for all those unknowns. If you cut through 4 or more members, you're going to have more unknowns exposed than you can deal with, okay? And keep in mind that every single member you cut becomes an exposed compression or tension force. Now, I typically assume on these truss problems that everything's in tension. Any negative value I get will confirm that is in compression. So as we draw our free body diagram, then you can also see what were the supports you might need to solve for. Sometimes it's none of them, sometimes it's one. It just kind of depends on what the truss is doing. So you can kind of backtrack, solve for those supports that you need, and then come back and start then solving for the required members. Now keep in mind, method of joints and method of sections are separate tools, but you can use them on the same problem. Okay, just because you use method of sections on a problem doesn't mean you can't follow up that computation with a method of joints computation. Okay, they're just two slightly different tools in your toolbox that fundamentally do related things. They just do them in a little bit different way. But you can select one and then select the other, just depending on what's the most efficient pathway toward your solution. You can also technically, if you want to, do one cut, solve for something, reassemble your truss, and go take another cut somewhere else to create another free body diagram, right? Remember that each and every free body diagram that you create has its own set of independent three equations that go with it. Okay, so a new free body diagram comes with new equations, which should give you plenty of equations to solve for all the unknowns. Let's go ahead and wrap an example into this video, just package it all up as one. So here's the truss that we're looking at, a large triangle. There's going to be a center, they call this a king post in truss vernacular, and a couple of other members there and there. Naming these points, we're going to go with A, B here in the middle, C, D, E, and F. My applied forces are 1,000 newtons at joint A vertical. We have 3,000 newtons at F, another 1,000 newtons at E, 1,000 newtons at D, no loading at point C. And just to make our lives a little bit easier, I went ahead and solved for the reactions. We'd end up with 4,000 newtons at A, and then we have a pin over here at C, and 2,000 newtons and no horizontal force because there's no external loading. Okay, so once again, this is a roller, this is a pin, and then our geometry is defined by the fact that it is 2 meters essentially between all of these named points. Okay, so we have a total 8-meter wide truss, and the last geometry we need is an angle. Let's go with a 30-degree angle here between the lower chord and that angled piece going up through A, F, and E. All right, so there is our truss, and we're actually on this problem asked to solve for only one thing, and that one thing is the force in FBE. Okay, so we want to find, and I'll just go and call this BE. Okay, find the force in member BE. Now you could label these if you want as F sub BE, or just with the member itself, right? But we're looking for the force in BE. All right, so as we think about cuts, I'm going to kind of ponder a few different cuts here. None of these cuts would be my final cut. Okay, so if you want to pencil them in or whatever else, but the first one I would consider is, say, this one, right? It cuts through that member, which is great, but it cuts through 4 members, right? It cuts through FE, BE, BD, and also BC. Okay, so it gives me 4, probably not the best choice. Okay, so another cut that I could make is I could cut across the top here. Now, this is not, it's an okay cut as well. If you use the upper portion of the free body diagram from that cut, you actually end up with a method of joints problem, right? Because you basically just have one joint, which is joint E. And you have 1, 2, 3 unknowns with a method of joints problem, which is too many to solve for. Now, if you use the lower portion, which gives you everything else down here, you could actually then solve for these three members, BE included. So that would be an option. I'm actually going to choose to do a quick two-step option. And the two-step option, the cut I'm going to choose is going to come right through here. Okay, so I'm not cutting through the member that I'm solving for, but I'm cutting close to it. Okay, and close to it is going to give me the information I need to then do a method of joints computation. Basically, I'm going to solve here for the force in EF. That'll give me enough information to do method of joints here at E. Okay, so that's the technique I am going for. Let me zoom out here a touch so we can still see that truss. So we're going to solve for EF using this cut right here. And the free body diagram, I could choose left or right. I chose the right end for this one. To show you it doesn't matter which end you choose. Okay, so we didn't cut that member we're looking for. We cut 3 different members, and those 3 members here are EF, and then here is BF, and a third spot here is AB. And then I add all my external forces, 1,000 kilonewtons at E, 1,000 kilonewtons, sorry, not 1,000 kilonewtons, 1,000 newtons. Get these labels right. Newtons, newtons, and we had 2,000 newtons pushing up from that pin. Now, whether you choose to draw the member BD or you just kind of think that this is acting like a big rigid body triangle, it really works either way, right? We didn't cut any of those members, therefore we didn't expose their forces. So those can just go along for the ride. All right, so here again, we get to choose where to sum our moments about. And we look at our forces. We have AB, we have BF, and we have EF. And again, the direction I'm headed with this computation, I'm looking forward to saying, I want to do method of joints at E. So if I can solve for EF, that will give me 2 knowns, 2 unknowns at joint E, and I can move forward. And so if I want to solve for EF, I really look for the point where the other force lines of action intersect, which in this case is going to be down here at point B. So I'm going to sum my moments at point B. Now, as I think about what I want to do here with EF, I really have kind of 3 options. One is I could find a perpendicular distance, possible, but would take a bit of geometry to work through. I also could slide EF. I also could slide EF up here to joint E, right? Sliding the force along its line of action. That's also possible, but then I need to solve for my distance from B up to that point and then kind of cross that into the horizontal component of the force. Or I could slide it all the way down, and I kind of cut it off here in my drawing, but I could slide it down to A, right down over here in this other drawing. And if I do that, I already have the horizontal distance of 4 meters. I just need to find the vertical component of that force, but I also know that this leg here is 30 degrees from horizontal. Okay, so I'm going to choose that method. So to talk through those pieces again, I'm going to take R cross EF, and the R I'm going to use is going to be 4 meters. And I'm going to multiply that by the vertical component of EF. Now, the reason I'm using the vertical component is because I'm crossing this horizontal distance into a vertical component, which is the only part that will give me a moment. So we have that vertical component is the value of EF times the sine of 30 degrees. And then I have to think about positive or negative from the right-hand rule. And so if I slide my fingers starting at B over to A, wrap them down into the component of EF, which is going downward, you should get your thumb coming out of the screen positive from the right-hand rule. Additionally, looking back at this free body diagram of the other forces, the 1,000 Newton force comes right down through B. That won't create a moment. I do have a 2 meter distance times this other 1,000 newtons. I'll write these out line by line, just because I have better room that way. So this is going to be negative from the right-hand rule, times 2 meters times the 1,000 newtons. And then the last moment I have is over to the 2,000 newtons. This is going to be positive, right? Sliding my fingers from B over to C, crossing them into 2,000, which is going upwards. You should end up with a 4 meter distance and a value here of 2,000 newtons. And this equals 0, right? Sum of moments equal 0. We have one unknown, and we find that EF is equal to negative 3,000 newtons. Now, I assumed that EF was in tension over here. Therefore, I need to reconcile what's going on with this negative sign. So it's basically in a negative tension. So I could say, therefore, EF is equal to 3 kilonewtons in compression, right? So we found that our initial assumption of the direction of the force in EF was incorrect. And if you think about the type of tension or compression in these trusses, right? If this is a truss which is basically spanning some kind of, a wall system, say below here, and you have loading coming downward on the top, it should make sense that the bottom chord is always going to be in tension, and the top level here is always going to be in compression, okay? Because basically these forces are pushing down on the top, and so it's going to push all of these top pieces into compression, and the bottom one here is going to be in tension. The middle ones will be a mix. Sometimes being in tension, sometimes being in compression. So that gives us EF. So to go ahead now to create my last free body diagram that I'll need, this is at joint E. And adding my external load, I have 1,000 newtons at joint E. Of course, this is method of joints. I just learned that EF is pushing in compression at 3,000 newtons. I don't yet know my force in BE. I'm going to solve for it. Let's go ahead and call that just here BE. And then the last thing I don't know in this free body diagram, I also don't know what's going on over here with F. Let's see here. This is ED or DE. Forgive my habit here. I was just depending on the day. Sometimes I put the F's out front. We'll just go with the point names. Okay, so BE is an unknown, DE is an unknown. Noting I drew this DE in assumed compression. I drew it pushing on this joint E. All right, now there's two ways you could validate that DE is equal to 3,000. One of those is to go through and sum your forces in the X direction, and we end up with the 3,000 value cosine of 30, and we know this cosine of 30 because each of these angles here is 30. Let me complete these free body diagrams, sorry for my negligence there, by adding an axis system. Every free body diagram needs an axis system. So summing force in the X direction, we have positive X going to the right. So that one's going to be positive, and then we have a negative DE cosine of 30, all that equal to 0. Of course, you could divide both of these sides of the equation if you wanted to by cosine of 30. And what we really end up with is DE is equal to 3,000 newtons. Now, the other way we could have solved for that, besides using some of the force in the X equals 0, is really from symmetry. Now, if you do use rules of symmetry, you need to have two types of symmetry. One is symmetry of geometry, and two is symmetry of loading. Okay, but if you have both types of symmetry, you can actually use that as justification to say, hey, DE must equal 3000, because in this case, again, I have symmetry of loading and also symmetry of geometry. So once I have the value there of DE, I can get into my last equation, sum forces in the y direction. I drew BE assumed downward, so that will be minus BE minus 1000 plus, now I'm just going to go 2 times 3000, and this is going to be the sine of 30, right, taking care of the vertical component of both DE and also EF, and this equals 0, and then we can solve this out that FBE turns out to equal 2000 newtons. We got a positive value, so therefore our assumption of tension is correct. So FBE is equal to 2000 newtons in tension. All right, so just to review what we did in this example, we first recognized that we could take a multitude of cuts. Okay, so we chose a strategy and we stuck with it. Like I said, I think the other usable cut you could have done is to cut horizontally across the top and then use the entire lower portion. Could have given you equations to solve for BE. I chose to take a vertical cut, cutting 3 members, and I solved for EF. Okay, so I created a new free body diagram. I got new equations that came with that. I found out that EF was equal to 3 kilonewtons in compression. I then brought that down to a third free body diagram, which is method of joints at E, right? 2 separate tools, method of sections, method of joints, just using them one after the other if needed, and solved not only for the force in DE, which also could have been solved with symmetry, but also then solved for the force in BE, which is what I was looking for. Okay, so you'll find that method of sections problems are a bit of a choose your own adventure, but they do give you that flexibility, and you do, after you work a few of them, kind of start seeing some pathways, some easy strategies to solve as few equations and few free body diagrams as possible. Hope you're having a great day.